Okay, so now let's try to prove this theorem regarding continuity of a function f that I stated last time. So remember, we defined continuity in the following way. We said the function is continuous at a certain point, as long as whenever I take a sequence of numbers on x-axis which converges to the point of interest, then the sequence of corresponding y values converges to the value of the function at the point of interest. And we said that the following theorem is true, that f is going to be continuous at x0, as long as for any epsilon there exists a delta such that if x minus x0 is less than delta, then f of x minus f of x0 is less than epsilon. So let's prove this fact, and because of if and only if statement, we have to prove this, actually two facts, implications going both ways. So proof of the theorem. So number one, I'm going to prove it backwards. Suppose for any epsilon, there exists delta greater than 0 such that x minus x0 less than delta, that implies f of x minus f of x0 is less than epsilon. All right. Now I'm going to choose, so I need to check that the definition of a sequence is going to hold. Definition of continuity is going to hold. So I'm going to choose any sequence xn such that the limit as n goes to infinity of xn is equal to x0. And so what we need to do, we need to show that the limit n goes to infinity f of xn is equal to f of x0. Okay, fine. So we need that. Well, how would I show that the limit of f of xn is equal to f of x0? I can use the definition of the limit, right, of a limit of a sequence. So I'm going to choose any epsilon greater than 0. And I have to verify that I should be able to find capital N, such that if n is bigger than capital N, then f of xn minus f of x0 is less than epsilon, right? All right, so if I choose any epsilon greater than 0, then by our assumptions, right, for any epsilon greater than 0, then there exists a delta greater than 0, such that x minus x0 being less than delta will imply that f of x minus f of x0 is less than epsilon, right? That's what we assumed in the beginning. Okay, so we have that. But also, so in addition, because the limit n goes to infinity of xn is equal to x0. Now, what does it mean that the limit of xn is equal to x0, it means that for any number, I can make, for any fixed positive number, I can make xn minus x0 less than a number as long as I make n sufficiently big. So therefore, there exists a capital N in R such that if n is bigger than capital N, then xn minus x0 is less than, and now I want to make it less than delta, right? So once again, because the limit of xn is x0, I should be able to find capital N such that if n is bigger than capital N, then this should hold. So, but then if xn minus x0 is less than delta, well, then xn satisfies this condition, right? And if xn minus x0 is less than delta, then f of xn minus f of x0 is less than epsilon. So therefore, from here it follows that f of xn minus f of x0 is less than epsilon if n is bigger than capital N. Right? So once again, I used two facts. I can make xn delta close to x0 because xn converges to x0. And if xn minus x0 is less than delta, then f of xn minus f of x0 is less than epsilon, right? Because of my assumption. And so if there exists a capital N such that this is going to be true for any epsilon, so the conclusion is that the limit as n goes to infinity of f of xn must be equal to f of x0, and we're done with this step. Now, step number 2. Let me suppose on the contrary. So, not on the contrary yet, so I'm moving backwards. Suppose a limit n goes to infinity of xn equal to x0. Suppose that this implies always that the limit n goes to infinity f of xn is equal to f of x0. So the function is continuous at the point x0. And let's assume on the contrary that the statement of a theorem doesn't hold. All right, so what does that mean? Theorem says that there exists an epsilon, well, is that for any epsilon greater than 0, there exists a delta greater than 0 such that this is true. What is a contrapositive to this? If I'm saying contrapositive to all epsilon being, to something being true for all epsilon greater than 0, contrapositive to that will be there exists an epsilon greater than 0 such that, okay, so previously we were saying that for any epsilon there exists a delta. So now the contrapositive to that would be, is that for that choose an epsilon that we got, such delta does not exist. So that means that for any delta greater than 0, the opposite of what we were saying before is true. If, so before we were saying that for all x minus x0 being less than delta, something is going to happen. So now it's not going to be for all, but for some. So there exists x delta such that x minus x delta minus x0 is less than delta, right? But this doesn't hold for that x delta. And what means this doesn't hold is that the difference must be greater or equal than epsilon. So, and f of x delta minus f of x0 is greater or equal than epsilon, right? So again, opposite to saying for all deltas means that there exists a delta uh, such that there exists a delta such that there doesn't exist a delta greater than zero such that my conclusion is true. So therefore, that means that for any delta, there exists an x delta such that whenever this thing holds, this doesn't. So greater or equal than epsilon. Okay, so this is our contrapositive. And so we're going to assume that the contrapositive holds. Right? All right, so now because this is true for any delta, uh, we're not going to look at special deltas, not all of them. So consider delta n equal to 1 over n. So then if I rephrase the statement, I can rephrase it as follows. There exists an epsilon greater than 0 such that, now, this was true for any delta. So if I use just deltas that are equal to 1 over n, then for any n in n, there exists, right? So my delta now is 1 over n. So there exists xn such that xn minus x0 being less than my delta n, which is 1 over n, this still gives me f of xn minus f of x0 greater or equal than epsilon. Right, so let's digest this once again. The previous contrapositive statement was true for any delta greater than 0. So instead of looking at any deltas, I'm just going to look at deltas equal to 1 over n. So therefore, for any delta greater than 0, I can replace that I have for any n in capital N. In fact, I am missing for any. Let's add it here. For any n in capital N, so for any delta n equal to 1 over n, there exists x delta, so I can relabel it as xn, such that if the difference between that xn and x0 is less than delta n, which I chose to be 1 over n, the same conclusion as before holds. All right, so we have this. What can we conclude from this? From this piece, I can easily conclude that the limit as n goes to infinity of xn must be equal to x0, right? Because when n goes to infinity, xn minus x0 is less than 1 over n. So by comparison, 1 over n goes to 0. So that means that xn minus x0 goes to 0. And that means that the limit of xn is x0. So this is true by comparison. All right, and then because of that, what I can conclude, because I assume that my function is continuous, right? So function is continuous, definition of continuity at x0 holds as long as xn goes to x0, then limit of f of xn must be f of x0, right? So therefore, by continuity of f at x0, I get that the limit n goes to infinity f of xn is f of x0, which I assume to be true in this case. All right, so that's fine. And what this means, in turn, is that for any epsilon greater than 0, there exists capital, let's say, N1 in R, such that n bigger than N1, this would imply f of xn minus f of x0 is less than epsilon, right? Okay, but now if I appeal to this, what do I know? I know that f of xn minus f of x0 is greater or equal than epsilon for all n. So in particular, it's greater or equal than 0 if n is greater or equal than epsilon if n is bigger than n1. And then if n is bigger than n1, I have that the difference must be less than epsilon from here, and it must be greater or equal than epsilon from there, which is a contradiction. And so we're done. Then the contrapositive that we assume to hold in the beginning is not going to hold, so that means that the condition, that our conclusion actually holds. So therefore, the summary of this is that we now have two definitions of continuity. One definition of continuity is this epsilon delta definition that I have listed here. And a second definition of continuity is the original definition that I gave that involves sequences. And you can use either of the two definitions to prove continuity, and depending on the context or the situation, one definition might be easier than another one. So you have to be aware of both. Both are going to be useful. So let's do a couple of examples. So example one, I show, or rather prove, that f of x equal to x squared plus t is continuous at x equal to 1. So approach number one Now there are two definitions that I can verify, so let's try to do both and see which one is easier. Approach number one. Let's do epsilon delta definition. Okay, so if I want to use this definition, I'm going to start by choosing an arbitrary epsilon greater than 0. And what I would need to do is to find the corresponding delta. Greater than 0. Okay, so what I want? I want x squared plus 3, right? I'm trying to prove a continuity at 1, so I want that minus 1 squared plus 3 to be less than epsilon. Okay, what does it mean? This is the same thing as saying, if I open the parentheses, I have x squared plus 3 minus 1 minus 3, so that means that I want x squared minus 1 to be less than epsilon. Hey, let epsilon. All right, fine. So that means that I actually want absolute value of x minus 1 times x plus 1 to be less than epsilon. Uh, Now remember that for epsilon delta definition, I'm saying that f of x minus f of 1 is less than epsilon, that you should imply x minus 1 is, you should produce x delta such that x minus 1 less than delta would give me f of x minus f of 1 less than epsilon. So to get the value of delta, I need to discover a corresponding bound on x minus 1 that I can impose to guarantee this, right? So that means that I would like to solve this for absolute value of x minus 1, right? So this is the same thing as absolute value of x minus 1 times absolute value of x plus 1. This has to be less than epsilon. And of course, this is easy to solve by dividing by x plus 1. So this will give me absolute value of x minus 1 is less than epsilon over absolute value x plus 1. So it's tempting to then set delta to be epsilon over absolute value of x plus 1. But of course, this cannot be true because delta is a constant. And if I'm dividing epsilon by absolute value of x plus 1, then that means that delta is not a constant. It is a function of x. So, nope. Well, and not only that, but also if I'm dividing by x plus 1, for instance, if x is equal to minus 1, then I cannot even divide by x plus 1 anymore, right? Okay, so what are we to do? Well, if I want to prove this epsilon delta definition, then really I should only be concerned with the values of x. So because I'm trying to establish a continuity, continuity is a statement about the behavior of a function near a prescribed point. So that means that I want to stay close to the point. And if I want to stay close to the point, in this case, x equal to 1, uh, I can restrict how far x can deviate from 1, right? Because again, if we're looking at a picture, for example, like this, really, continuity only is interested in what is going on in the immediate vicinity of the point x0, right? Uh, and the value of delta, by the way, is not really unique because the delta that I shown in here really is an optimal delta, right? That's the largest possible delta that would work. But if instead I use delta that is equal to half of the length of the most optimal delta, so like the red parenthesis here, that delta would still work, right? Because as long as x is inside the red interval, f of x is going to be always epsilon away from f of x0, right? So the choice of delta is not unique. I can always choose a smaller delta and things would still work. Uh, so with this in mind, what I can try to do, I can assume, for instance, that x is going to be on a distance of no more than 1, that I want x to be on a distance of no more than 1 from 1. Uh, let me write this here. So now assume also that x minus 1 is less than 1, right? So I'm looking at my delta, for my delta, inside the interval of the distance 1 from my point 1. So if I assume that this is true, then, uh, of course, I can rewrite the same expression without using the absolute value sign. So add 1 to all 3 sides. This gives me 0 less than x less than 2. So x is between 0 and 2 if I force x to be inside this interval. And then if we re-examine the statement here, in fact, if I'm just going to copy it, well, so if x is between 0 and 2, that means that the smallest my denominator can be is when x is equal to 0. So then this must be less than epsilon. All right. So if I restrict x to lie between 0 and 2, then x plus 1 in the denominator over here is always going to be bigger than 1. And so therefore, the largest epsilon over x plus 1 can be, in this case, is that it can be less than epsilon. So therefore, if x minus 1 is less than 1, we have x minus 1 being less than epsilon, right? So if this is less than epsilon, then I can follow the chain of inequalities over here backwards. And I have this inequality. So this would imply that f of x minus f of 1 is less than epsilon. Okay? All right. So, but then if both this and this condition are satisfied at the same time, so this is equivalent to saying if x minus 1 is less than 1 and epsilon at the same time, then x minus 1 is less than the smallest of these two, minimum of epsilon and 1. This implies f of x minus f of 1 is less than epsilon. So then this guy here, minimum of epsilon and 1, is my delta. So I proved the existence of delta such that if x minus 1 is less than delta, then f of x minus f of 1 is less than epsilon. And so I'm done. So I verified the epsilon delta definition. Well, let's try approach number 2. And here we're going to use a sequence definition. All right, so I'm going to choose any sequence xn such that the limit n goes to infinity of xn is equal to 1, right? In this case, we're looking at continuity of the function at 1. So then, if I take a limit n goes to infinity of f of xn, what was f of x? F of x is x squared plus 3. So this is the same thing as the limit right? And then immediately by properties of limits, how can I write this? I can write this as a limit n goes to infinity of xn quantity squared plus the limit n goes to infinity of 3. And the limit of xn is 1, so 1 squared plus 3. And what is 1 squared plus 3? This is exactly f of 1. So if I take a sequence, the limit of which is equal to 1, then the limit of f of that sequence is f of 1. Okay, so then f is continuous at 1. That's it. That's the proof by using the sequence definition. Why is the sequence definition dramatically simpler? In this case, because I ended up using properties of limits that we verified before, properties of limits of numbers. And that allows me not to get involved into these epsilon delta discussions, because all the dirty work was done before when we proved properties of limits. So in this case, using the sequence definition is significantly easier than using epsilon delta definitions. But in certain cases, we'll see in the future, using epsilon delta definition actually is going to be much superior to using the sequence definition. And typically, it is going to be superior to the sequence definition in certain proofs. And so next time we're going to continue discussing continuity.